Good afternoon. Today I would like to present some results we obtained recently for the quenching behavior of the solution for the problems with sequential concentrated source. Now the problems that we are investigating are formulated as follows. We let alpha less than or equal to 1, T tutor, capital T, A, B, C, and D be positive real numbers. We let the alpha, L alpha of u be the operator, which is equal to the first time derivative with respect to the time of the solution u minus a special differentiation of the u with respect to the time t, and then differentiate twice along the x direction. Now this function is known as the diffusive operator. The domain that we are going to consider is just an interval from 0 to a. Now for simplicity, we can think of this is just a rod on the one-dimensional case. Now for positive integer capital N, when the k from 1 up to capital N, we let the tk equal to the k times the t tutor, which the t tutor means that the time steps for the energy going to impose into the system. We consider the problem in this particular form. The left-hand side is the so-called the diffusive operator, and on the right-hand side is so-called the forcing term. And this forcing term will be divided into three parts. One is the parameter for d, and the other is the summation of the Dirac delta function, and the forcing term, special forcing term for the f of u on the right-hand side. Now, during our study, we always can think of the solution u as the temperature distribution on the rock, and a forcing term is some sort of energy sources. For example, there is a chemical reaction so that the heat generating inside the region. Right here, for simplicity, we assume the initial data is identically equal to 0 for all time, and also the two ends of the line will keep to be 0 as well. Now, so that if we have the forcing term inside, it means that the energy will be generated from inside and then diffused to the two ends of the line. For the Dirac delta function on the forcing term, since this is a singular solution, so it means that due to this singularity, we always assume the solution used to be just a continuous function rather than the continuous differentiable functions that are in the classical sense. And also, because of the special nature of the f of u, when the u go to c, the f function will become infinity. So what does it mean is that we may have a special case that we have the right-hand side become unbounded when the time go to a certain finite period. And if that happened, we call the solution quenches in a finite time. Now, let us have a closer look on the left-hand side of the operator. The operator right here is called the Riemann-Liouville fractional operator, which is defined as the derivative of the integral of function with weight function t minus s in certain power. Now note that in particularly with the alpha equal to 1, this term become 1. But then it will back to the classical derivative defined by Newton form, which was developed 400 years ago. Now this operator is a better approximation for the diffusive behavior of the mean square displacement for the Brownian motion. In particularly, is on the slower than normal timescales diffusion. In our case, we can think of the temperature distribution on the line, which is made of porous medium material, and the temperature is diffusing along with different rate. More precisely, since two ends keep to be 0 of the typical temperature, so it means that the the heat energy will diffuse to the both ends of this line. Now, if there are microscopic pores with lower conductivities filled inside the original material, the heat transfer will experience different diffusion rate. So it means that the heat distribution will no longer be smooth and even on the line, so that it will make the energy consumption become difficult. This uneven heat diffusion on the rock is named as a subdiffusive properties. Now, many results are obtained due to these special properties on the material. So now let us have a look on the right-hand side of the equation. On the right-hand side of the equation, besides the parameter d that we will discuss later on, the direct delta function can be interpreted as an energy source, which is stationary at a particular position. Now notice that because of the diffusive properties of the material, so the temperature inside will be grow not only at this particular point source, but also to the surroundings. Due to these properties, several special results are obtained by the following authors. Now recall about the so-called subdiffusive material. Now the diffusive rate is lower than the normal scales. So it means that the energy can be accumulated much higher, and hence the unboundedness of the forcing terms is more likely to occur. Now when this happened, the quenching phenomenon will come out. Furthermore, the energy right now plumbing into the system is not only just once. It comes out to be at each time steps, the extra energy are coming into the system as well. Now, this type of energy surprise is simulated by considering the real-world condition that the changes of the energy surprise are too fast when compared with the whole process. So therefore, all those energy sources come out will appear in the impulsive form. So that is the way that why we impose the problem in this way. Now we are ready to give the form of the solution that we may have to satisfy this equation. The solution of the problem will depend on the form so-called the Green's function. Now, the Green's function plays an important role on showing the existence of the solution. In our subdiffusive cases, it is a multiplication of the heat operator with a special function g alpha of z, which is known as the Menindee function. Now this function is greater than or equal to 0 for all z greater than or equal to 0, with the total area, total energy together is equal to 1. And most importantly, this function will go down to 0 exponentially when the z go to infinity. In particular, when we join this with the classical Green function, which has an exponential part that is appear in this particular form, so we integrate the Menindee function with the exponential function, is come up to another interesting function so-called the Meta-Lafat function. Now this function is a generalization of the exponential function in our classical analysis. Note that G1 is the Green's function for the heat operator. So now we are able to rewrite the solution into the particular integral form that is including the integration of the Green's function in the alpha degree multiplied with our forcing term f of u. So next, we are ready to give some main results. But before that, how about we're going to go for several theorems we can obtain by using the standard analysis method, such as the maximum principle in our partial differential equations. Now, the first theorem we have is that the solution u satisfies the equation that we mentioned before is an increasing function with respect to the t strictly less than capital T. So it means that during the existing time, the solution is increasing with respect to the time t. Now, since we have the energy source inside the system, so the temperature arises, well, it seems to be very logical. And the second theorem we are going to have here is concerning about the relationship between the d, that is the parameter of the forcing term, with the solution itself. Now recall that since this coefficient is appear on the forcing term, larger the d means that you have a larger forcing term. So larger the forcing term, we have the larger the solution. So that is what we have proved here, is that if we have the larger coefficient d1 greater than d2, then the corresponding function u sub d1 should be greater than or equal to u sub d2 within the region of our consideration. Finally, according to the keeping zero at the two ends on the line, due to the symmetry, we expect that the maximum temperature will occur at the center. And that is what we prove, is that the maximum value for the function is always obtained at the point x equal to a over 2. It means that it's just in the middle of the rate that we are going to consider. These theorems can help us on comparing the so-called upper or the largest and the lower or the smaller solution of the problem. By use of the upper and the lower solution for this problem, we are capable to show that whether the solution quench or does not quench. We are now give the main results as follows. So take a look on the problem itself. Because our problem, there's a diffusive properties on the left-hand side. And since the material filled with the subdiffusive properties, so it means that the energy diffuse slower than the normal scale that we have. On the other hand, on the right-hand side, we have a certain kind of the temperature source. It will make the temperature increase. But because of the temperature around the boundary is remained zero, so there is a competition between the energy generated inside or diffuse it out to the boundary. Now the first result we have here is that if we put large enough energy inside the system, it will make the system quench. Certainly, it's because on the D be large, it means that we have largest force inside. So this means the diffusive behavior cannot be take place good enough to make the system cool down. Now remark of this, if we have the maximum occur at the center a over 2, so it means that if the solution quenches in a finite time, that will be the quenching points that we have. On the other hand, if D is small, then the diffusive property will dominate the temperature distribution, and hence quenches does not occur. Now this is the case that we see that the solution will remain bounded away from the C all the time, so that the right-hand side of the equation will always be a finite situation. So this will make the system go up to T tend to infinity. Now combining these two results with the results that we have before, we notice that there is a D star, we can call it to be the critical D, such that the solution U quenches in a finite time when the D is greater than the D star. And on the other hand, U will be bounded away from C for all time when the D is strictly less than the D star. Now, another direction on consider this problem is that since we have so many point sources inside the system, so how frequent we will put in the energy will make the condition will be different. So in this paper, we will consider what happened for the T sub k related with the D. And also, there will be a competition between the D with the TK. For example, when D be small, normally it should be bounded away from the C all the time. But in the meantime, if we have a fast enough or more frequent sources inside, then the solution will quench in our situation. As a very quick extension of the result to infinite domain, that is the domain from negative infinity up to positive infinity, we have the integral representation form for the solution U as usual. But since right now the Green's function for this dimensional space will appear as the exponential form, so it looks similar to what we have for the interval situation. So a similar result obtained that there is a D star such that the solution will quench or does not quench, depends on the D is greater than D star or less than the D star. Another direction we will come up to be the picture is that what may happen if we have the diffusion slower than the standard case. Well, we do not have a good answer for that yet, but we will working on it. Hopefully, it will be finished recently. So we are now conclude our result right here. We are considering a diffusive problem that we have on the line from 0 to 8. And this diffusive problem will have a forcing term, so-called the energy generator, on the right-hand side of the equation. And most importantly, the energy generated is in the form of the impulse type. And right now, if the solution U reaches a certain point Z, such that the f of U will become infinity, we call this to be quenching. So when quenching occurs, it means that the whole system will blow up it will no longer exist. Now, in our case, is that we find the condition that we have a critical value d, such that when d is smaller, the solution will be exist for all time. But on the other hand, if the d is greater than this critical value, the solution will quench in the finite time. Okay, so this concludes what I'm going to present to you, and thank you very much for your listening.